Here, and we are live. Welcome everybody to Ask the Astronomers here at Astronomy at the Beach 2020, which is an online event. Tonight we're going to have three panelists, and you can ask them any questions you like. David Levy is going to be on our panel. He's running a pinch late with other talks. But he will be joining us. He's author of 35 books and other products. He won an Emmy in 1998 for writing a team in the Discovery Channel documentary 3 Minutes to Impact. As a science editor for Parade magazine, 97 to 2006, he was able to reach more than 80 million readers, almost a quarter of the population of the United States. A contributing editor for Sky and Telescope magazine. He writes the monthly Star Trails column, which I say is a very good column. And his Nightfall feature appears in each issue of Canadian magazine Sky News. Our second panelist, who is actually here, is Jane Huang. I get that right? Is a NASA Sagan Fellow in the Department of Astronomy at the University of Michigan. Go Blue. Her research uses state-of-the-art radio telescopes to map the dust and molecules orbiting young stars in order to explore the conditions under which planets form. She's receiving her PhD in astronomy and astrophysics from Harvard University. And last but not least is Dr. Larry Lebofsky. He's a senior education and communications specialist at the Planetary Science Institute and an education specialist at the University of Arizona. He has a Bachelor of Science in Astronomy from California Institute of Technology and a PhD in Earth and Planetary Sciences from MIT. Prior to joining PSI in 2008, he was a senior research scientist at University of Arizona's Stewart Observatory and Lunar Planetary Laboratory. Boy, that's a lot of words. You know, it goes on with lots of things. Larry's done a ton of stuff, okay?
What happens when you've been around for 30 or 40 years, so yes.
Yeah, go to the Astronomy at the Beach 2020 site and look up the event, and Larry's got a ton of stuff, plus some websites you can look up on him. Our moderator is supposed to be Adrian Bradley, who is the president of the Great Lakes Association of Astronomy Clubs. One of our sessions is running late, and he will join us in a few moments. Bob Tremblay is actually, he's a NASA solar system ambassador, and he's going to be joining us in the chat session to take some questions from people. So everybody, it is now up to you. Offer some questions up to these fine folks. I'm just a simple moderator. I run the computers at U of M. Do we have any questions so far? Bob, I'm gonna pin you on something. I see there's we have 6 concurrent viewers that are out there, so I know there's people out there you're viewing. Well, let me think of something good. Since we're dealing with radio telescopes, Jane, how did you get into that? Radio telescopes isn't exactly something you buy at a department store.
Right. So I was actually a chemistry major as an undergrad at University of Chicago. And that's sort of when I learned about the field of astrochemistry, which, like, you know, when I was a kid, I didn't know that you could find pretty large molecules in space. I thought space was just, you know, hydrogen, helium, very simple stuff. Because space is very cold, one of the best ways to find molecules is through rotational spectroscopy. So molecules rotate and then they emit at characteristic wavelengths. And it just so happened that right before I started grad school, an international group of astronomers had built together this really powerful telescope called the Atacama Large Millimeter Submillimeter Array, which is up in the plateaus in Chile. And anyone in the world can use it. They have, you just write proposals with your project idea, and then they have a team of professional astronomers evaluate your proposal and decide which ones that they're going to schedule.
Cool. Bob put forth a question. And I'll leave it to any one of you three of us. Does dark matter make you as crazy as it makes me? I see Dave snickering and Larry snickering. So
yes. Me personally, I study rocks in space. So big, medium-sized rocks like asteroids and airless bodies and icy bodies, down to rocks on the Earth like called meteorites. So dark matter is something that interests me, but I have no clue what's going on. I'll admit that. I am a geologist who studies geology in space, basically.
I think
You're muted,
David,
David.
you're muted.
Let
David,
me
you're muted.
unmute.
Yep,
Hi,
you've
Larry.
unmuted. Excellent.
Okay, thanks. Larry, I think that Gene Shoemaker would be very proud of what you just said. And I'm wondering if you still have the 1 series license plate on
Still
your
do.
car that you had when I was working with you.
Yep.
Dark matter and dark energy are very interesting concepts, not so much for what they are, but for what they mean. In fact, if dark matter and dark energy are real, the universe is far more massive than the regular matter gives it credit for, and the regular energy, then it definitely is powerful enough that it will expand forever. However, nobody's detected it, and for sure. So we don't know. We know that it may be there and it may not be there, but it's a little bit too esoteric for my day right now. And so that's all I can say right now about dark matter and dark energy, except let's keep looking around for it. See if it knocks on our door one day.
Well put.
Thanks.
We got a question from Dale Parton. He was a speaker last night, actually. From what distance could we reasonably detect radio signals from another civilization? From 100 light years? From the whole Milky Way galaxy, as often assumed in the Drake equation?
Adrian, why don't you try that one?
So, all right. So, repeat the question, Jeff. You're
This
gonna
is
love
from,
my answer.
This is from Dale Parton on the YouTube question. It says, from what distance could we reasonably detect radio signals from another civilization? From 100 light years? From the whole Milky Way galaxy, as is often assumed in the Drake equation? Question mark.
All right, I'm answering this one. If mathematics says that radio waves will exist and make it as far as the width of the Milky Way, then, you know, who's to say that we wouldn't detect life? But the question is, would we pick up the signal? Would we understand the signal that came in? Is it from life, or is it from other, some naturally occurring activity that's going on? So me not being the professional, my common sense answer to the question is, I think it's possible. And again, I think looking at, if we're not sure from experience and from being able to test it, you have to look at the mathematics to see if it says it's possible. So there you go.
Part of the limitation, besides how long it takes for the signal to get here, is the strength of the signal. So if it's a really, 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 really powerful signal, then yes, you could detect it across the galaxy. But if it's, you know, something that's weaker, just like hearing radio waves from the Earth, and as the old thing is that, you know, people out there are watching our TV right now, then if it's a weak signal like that, then you're probably talking about only hundreds of light years away.
One of the things I think all of us can agree on, however, is that you have posed one of the most central questions in cosmology today. And it's one of, not just across cosmology, but across all of humanity. Are we alone? Are we, with the universe as beautiful and as big as it is, are we alone? I think that is one question that I would love to see answered during my lifetime, although I highly doubt that will happen. Good question that you asked.
Yeah,
Yeah,
what
Bob?
one
Go ahead. Go
one
ahead.
thing I just wanted to add is, as far as naturally occurring radio signals go, astronomers' instruments can detect things from outside our galaxy in other galaxies. But those are radio signals produced by really powerful events, such as like supernova, stars exploding. So it's not clear whether a civilization can create a signal that's that strong.
You may want to watch the movie Contact, which in fact I may want to watch it in the next day or so, but that explores that situation and it does a pretty darn good job of it. And you may want to, and it's fairly, not entirely, but fairly accurate. And a lot of it is filmed at the Very Large Array, which is a real radio telescope observatory in New Mexico. And you may want to watch that and see what they have to say about it, because they suggest a possible answer.
Bob Tremblay added, I thought that the inverse square law would mean that it would be hard to distinguish our radio from background noise after several tens of light years.
Absolutely, it would be.
Oh, yeah.
Yeah, so I think, Larry, I think you were mentioning if the signal's not strong enough, then it would be indistinguishable from other signals.
Background noise, yes.
Background noise that's basically what that is. So, all right, we do have another question. I'm kind of stealing Jeff Koopmanis's thunder. Thank you, Jeff, for getting it started. By the way, he deserves a round of applause for getting it going on time.
Thank you, Jeff.
And
nice meeting you.
All the work
you too, Dave.
doing. Yeah, so I'm inviting you to hang out, and you're going to get one of these questions since you set me up with one. You can answer this one. Do you think matter keeps going both infinitely large as well as small? From Patrick O'Rourke. All right, Jeff, what do you think?
Frankly, I'm not a physicist. I'm a IT guy. And I would have to say things probably go both ways. They're making progress in all of those, what is it? Not neutrinos, it's the things, the muons and all the subatomic particles. So they keep discovering things there. And, they keep discovering things that are super huge, like some of the universe-wide I don't say rhythms, but waves and gravity waves, things like that. So I would think it'd go both ways. But this is an IT guy and an amateur astronomer that you're talking to. So, and with that, I do have to bow out. I have a session myself to give at 8:30. So I'm going to get out, and thank you for putting up with my incompetence for a little bit and chitter chatter. So you guys have
good luck on your session. We'll handle this one.
Yeah, I'm running solo on mine. So you guys have a great time, and thank you so much for becoming part of this, and reminding everybody to make sure you use the like button all you want, and leave lots of comments, and if you can, fill out that survey that's at the Astronomy at the Beach 2020 site. Thank you much, and I'm going to be bowing out.
Bye now.
All right.
And how do I do that?
You find your exit button. It's on the right.
Because I started the meeting. Actually, I got to give you.
No, give me the host.
Yeah, I'll give you the host. Hang on. Where'd he go?
That's obviously a younger Jeff Koopmanis from his playing days.
Yeah, when the tiger hat was still around. Right now, it's at the bottom of Ford Lake.
You gave up too soon.
Yeah. Okay. Have a great time, guys.
You too.
All right.
I will, and you do want to add that I'm very happy that Larry is here. He and I were working together for a number of years, from about 1992 on to about 1996, and we actually have become good friends over the years, and we don't see each other as much as we should, but we still are good friends.
Yes.
It's good to see you, Larry.
Good seeing you, David.
All right, so now let's pose that question to to the professionals here. So we've got a couple
Right.
questions coming in. So do you think matter keeps going both infinitely large as well as small?
So when,
Hey, Jane.
go on, Jane, yes.
Um,
We'll give you the tough ones.
so there's something called the standard model of physics that describes the particles that make up the universe. I think most of us are familiar with electrons and protons, which are already pretty small. But there are also, I think a few years ago, we discovered, not we, CERN discovered the Higgs boson. But you can't go infinitely small forever. There's a limit to how small things can be, and I think that's called the Planck length. And as far as how big can things go, the things cannot become infinitely large either, but we do get very large scale structures in the universe. So galaxies are in groups called clusters. And so there's some coherent structure on very large scales in the universe.
And we're finding that some of those structures are very, very large. But, hundreds of, well, tens of millions of light years, and I'm not sure hundreds of millions of light years across. But yes, I'm trying to think about some of the large scale galaxy structures.
Yeah. What's the one thing that's interesting is that the word filament is used to describe both the little tiny thing that lights up a light bulb up here, that's lighting me right now, and the largest known, excuse me, the largest known structures of superclusters of galaxies in the universe. The Perseus to Pegasus filament, for example, is a gigantic collection of superclusters, voids, and other structures or lack of structures of galaxies. And although when I was just studying the Wikipedia article on filaments, they said that it was discovered by some astronomers in the 1980s. Not really. I think it was first detected by Clyde Tombaugh when he was looking for extra trans-Saturnian planets, and he picked it up, and he was just amazed at the structures he was finding there back in the 1930s. So filament's an interesting word that refers to a lot of things, including these gigantic megastructures that we're now finding in the cosmos.
All right, so let's get some more of the questions. We've got a few of them in the chat now. We'll start with Same Old Dog, who asks, what is happening presently with the calculation of the Hubble constant?
Oh yeah, that's a good one. So so the Hubble constant tells us something about the expansion of the universe, and there are a couple of different ways of measuring it. So a team, I think led by Adam Rees at Johns Hopkins, who was also one of the Nobel Prize winners for discovering the evidence for the acceleration of the expansion of the universe, they use something called type 1a supernovae. So supernovae are stars that explode, and their brightnesses are very predictable. So they're useful for figuring out how far. So if you see a type 1a supernova, you can figure out how far away it is because you understand the underlying physics. And they get one number for the Hubble constant. And then there's another team of astronomers. They use something called, they use the cosmic microwave background measurements from things like the Planck satellite. So they use something called baryonic acoustic oscillations to calculate the Hubble constant, and they get another number. So the numbers are not that far apart. I think right now it's about 68 or 72, something like that. And at first, I think astronomers were maybe not so worried, because you have to remember that every time you make a measurement, there's some noise. And then some astronomers thought, okay, it's just noise. They're really the same. But both teams kept making more and more measurements, and then the error bars kept shrinking. So recently, there was a third way that was discovered of measuring the Planck constant, not the Planck constant, the Hubble constant. And this is using gravitational waves. And this is great because it's completely independent of the first two methods. And the reason having multiple methods is useful is because sometimes there's something called systematic error, where you're either not properly accounting for an error in your instrument, or maybe something in your model is not correct. So somewhat unhopefully, the number that people got with the gravitational wave method is that it fell smack in the middle between the other two methods. But their error bars right now are so big that that right now it's consistent with both measurements. As people make more and more gravitational wave measurements, those error bars should shrink, and then hopefully that should be able to distinguish between the two possibilities. And so there's a lot of debate right now about why those numbers are different. Again, there are some astronomers who think that one of the teams might just be having some sort of source of systematic error. But if both teams are right, then that means that there's something missing in our understanding of the physics of the universe. Because one set of measurements is sensitive to what conditions were like in the early universe, and another is more sensitive to conditions in more recent history. And we think we understand how the universe evolves, but if both of those numbers are right, then something has to be a little bit off.
Mute myself. We'll go to unmute myself, and now we have.
You should know better.
Professional astronomers and one amateur does it take to unmute a button?
Yes.
And
I would expect that of us, but not you.
Right. I do also work in IT, but sometimes you get tired of typing on computers. It just happens, which is why I'm also a photographer. Let's go to some a couple of questions back to back by Dale Parton, and related to the Perseverance rover and Mars. He says, it's disappointing to me that Perseverance can only drill a few centimeters into the surface of Mars. I suspect that over long periods of time, cosmic rays would sterilize that depth. He wants comments on that, and any thoughts on why Perseverance does not have an instrument to directly look for life on Mars. So who wants to take that one first?
Let's just Larry do that.
Thank you, David. You're good at it. Well, not knowing the details of the instrument, there's a limitation to how far you can drill down into a surface. I mean, just think about having a drill on the Earth, and I thought Perseverance could go down more than a few centimeters. I'm not, but I could be wrong about that. But things like cosmic rays do not penetrate very far down. So cosmic rays, in fact, you can tell how long an object like an asteroid, or if you get a meteorite on Earth, you can tell how long its original parent body was out in space by studying the cosmic rays, because the cosmic rays are literally just, think microns into the surface. So they won't, whatever is, drilling down into the surface of Mars would not be affected by cosmic rays, as far as I am aware of. There might be other issues, but not cosmic rays.
Okay.
We really don't know where life might be on Mars, although
That is a correct statement.
Carl certainly suspected it, and I think a lot of us do. And now with this thing on Venus, what kind of life we might look for in its atmosphere is another question. But But we really don't know where life would be. We suspect that if it does exist on Mars, it's pretty close to the surface. And so Perseverance should be able to get down to a level where there could be life if there is.
And again, it depends on its life as we know it. There's always that caveat. And would we recognize something that prior to finding it, we, not understanding what we're seeing?
Yeah, very true. All right, so I must read Bob Trembley's question. Anyone else think the very large scale shape of the universe looks uncomfortably like a neural network?
That's a computer question.
Yeah, I think that would be one for
answer
Adrian.
that one. Yeah, or maybe we designed our neural networks to look more like the way the universe is already designed. Kind of, well, how it's already been set up, how things work. That looks great. We'll call that a neural network.
Yes.
And we just sort of follow along with that design. That's my take on it.
I'd like to offer something about one of the words you chose in that very good question, which was the word design. George Wald, a Nobel Prize winner from, I think, the 60s or 70s, gave a lecture, it might have been his Nobel Prize acceptance lecture, called Design in the Universe. And he says a number of things that allow life to be possible. One is that ice floats. Therefore, life is possible. He goes on to say that if ice did not float, if you dropped ice into water and it just sank to the bottom, then life would not be possible, because the first time that life formed in water and water froze, the ponds would freeze solid, and then the life in that pond would be gone for the rest of the winter and would have to reform the next season. Another thing he said in the same lecture was that the night sky is dark. And if the night sky were not dark, if the reason the night sky is dark is very profound, and that is that the light from the farthest objects in the universe hasn't reached us yet. If the night sky weren't dark, then all the light from the universe would have reached us, and the universe would be uniformly as bright as the sun. Every square degree of sky would be as bright as the sun, and we would not exist. But because all the light from the universe hasn't reached us yet, the night sky still is dark, and we can look out in the sky and see it. And that's what George Wald has to say. And I think that's fairly profound. I think that people like George Wald and Carl Sagan have said some amazing things about the possible existence of life elsewhere in the universe. We do know one thing for sure, that it does exist here. We don't know if it's intelligent or not, but we know it does exist here on Earth.
Yeah. All right. Any additional comments, Jane, on that, or ready for the next question?
Well, I would just say that there are a lot of shapes that recur at different sizes throughout the universe. I think David mentioned filaments. You see huge filaments connecting galaxies and small filaments here on Earth. And I think that just makes sense because physics operates at all scales, and some types of structures are just more efficient.
Yep, I would agree. All right, let's get a couple of these questions here. Let's start with Botanical. I didn't pronounce your screen name right. Botanicaladric said, Botanicaladric, I think. How do hot Jupiters in Mercury-style orbits affect our model of planet formation?
I think you're the expert on that.
Yeah. So just to give some context to
The pieces when the very first
I guess we'll let Dave go because He's a senior member. Jane, you're going to go right afterward. I want to hear both of your comments on this. So go ahead, David.
Okay, one of the very first 51 Pegasi, I think, was one of these hot Jupiters that was orbiting its star in 3 or 4 days. And I think there are quite a few of those. And those are simply found because they're the easiest to detect. But we're now detecting, like in 47 Ursae Majoris, planets that are at much further distances. In fact, one that might have a moon that is Earth-sized. And I think the reason that we're seeing so many hot Jupiters at 3 or 4 day orbits is that they're just easy to detect. There are a lot of stars out there and a lot of planets out there.
All right, Jane, your turn.
Yeah, so when hot Jupiters were first detected in the 1990s, they definitely posed a challenge to planet formation models. Up until then, of course, the only planets we knew about were in our own solar system. And in our own solar system, all the inner planets are rocky, and you don't get gas giant planets until far out. So it was surprising that you could make such a massive planet that close to the star, that you could find such a massive planet that close to the star, because they thought that there just wasn't enough material there to make a planet that big. So there's still a lot of debate over how Jupiters are made. A couple different ideas. One is something called in situ formation, which is that the Jupiter forms at the hot Jupiter forms at the location where we find it. The other idea is that it is made further out, and then it migrates inward through a gravitational interaction with what's called the disk, which is all the material that's swirling around the star.
Okay.
And one addition to that is where Jupiter and Saturn and Uranus and Neptune are. It's not where they probably initially formed. That they have moved over time from their original positions and migrated in and then migrated back out again. So they have been interacting over time. And in fact, it's possible that, that some models of why Mars is smaller than the Earth is in part requires that the solar system had another Jupiter-sized or Saturn-sized planet that probably got, swung out of the solar system, ejected due to interaction with the other gas giants.
Yeah, in all of the videos I've watched, I think there's another theory that suggests, thanks to the presence of Saturn, it kept Jupiter from migrating too far in and wiping out the rocky planets. So they're thinking that with our, I guess, fortune of having two gas giants, gravitationally, it stabilized Jupiter to the point where it's in the orbit that it is today. Now, I don't have full details of it, but that I found that interesting, that movement of our solar system, and we're at a point where it's stable, and that it allows for life to form, and things that are happening now.
Basically you have models and you change the initial conditions a little bit and all sorts of things can happen. So you look at what you have now, create a model that matches what you see, and maybe that explains some of the things you see, but not necessarily all of them. So you come up with a different model and explains a few other things, but then all of a sudden, oops, it doesn't, it's inconsistent with something else we see. So people are refining their models of how the solar system formed and evolved. And, somebody will come up with another model in the, not too distant future. Yeah.
And it'll be on YouTube, and I'll watch that probably.
Yes.
I noticed that some of the ways that these theories get spread to the public via YouTube or rebroadcast of programs that that air, years ahead, and then there's live views of live broadcasts that are done with astronomers and astrophysicists basically sharing their information with us common folk over YouTube.
There's actually, sorry.
I was going to read a question from Kenneth Burton, who's in the Was Club. David, you know him well. How close to getting any idea of the composition of, how close are we to getting any idea of the composition of either dark matter or dark energy?
Not close at all, I don't think. But Jane, that might be more your field. I just don't see this happening in the next few years.
It's certainly an active area of research. I don't work directly in it. So the thing about scientific progress is that it's always hard to say until it actually happens, right? It's certainly been a subject of research for a few decades at this point, and there are a lot of smart people working in this area, lots of different experimental ideas. So I think we'll just have to see.
I think one of the interesting things looking at Larry's backdrop, I assume that you're not really over Machu Picchu right now, but
No.
this is a question that really goes back and back to the time that Machu Picchu was alive and filled with Incas who were looking up at the night sky, asking questions that are in some way similar to ours. And I don't think they would have used the word dark matter and dark energy, but they would have had questions that were kind of could actually reach forward through the eons to where we are right now. It's just a long, never-ending process. We go with the road has turns, we go back and forth. We don't know when we're going to know. And when we do know, there'll be a million other questions that we'll have to answer.
All right. So same old dog. I kind of skipped over your question. I knew I was going to come back to you. Same old dog says, where are the neutrinos? I demand to know. So
I personally do not have the answer to that one.
I mean, people are detecting them. There's something called the ice cube neutrino experiment. It's just that neutrinos are tough to detect because they can just, we describe things with like cross sections and intuitively something with a larger cross section, it's easier to detect because you think of a target that you can hit. And neutrinos just pass through everything very easily. So scientists who detect neutrinos even name their individual neutrinos because there's so few of them. But I mean, that is consistent with how we expect them to behave.
One thing I can add to what Jane has so wisely said is that when the supernova in the Large Magellanic Cloud in 1987 went off, it was preceded by several hours by a tremendous burst of neutrinos. I also want to say, in the time that Jane took to answer that good question, trillions, squillions of neutrinos passed through her. So they're there.
Okay, so I was about to ask a question concerning the recent dimming, brightening, and now re-dimming of Betelgeuse, and if the latest dimming of Betelgeuse is where astronomers are in trying to determine what could be causing this latest round of dimming. So,
I've been watching Betelgeuse a lot lately. It's out every night now. I think Orion rises at around 1 a.m. And I've been looking at Betelgeuse, and it's really active. It's going from being very dim, almost dimmer than Gamma Orionis, or even Delta Orionis. Mintaka might even be dimmer than that, too, getting as bright. Not as bright as Rigel, but it can get as bright as Rigel. But it has been flickering quite a bit lately. It certainly is active. So whatever's happening there, whatever dust is being emitted from the surface of the star, it is affecting the brightness, and Betelgeuse is changing quite rapidly right now. Does this mean that it's going to be a supernova in the next few weeks? No, it does not. Sadly, it does not. It would be nice if it did, but I don't think it's going to go off that quickly. Has it gone off? That is another question. It may have already become a supernova, and we just need its light to spend the 500 or 600 years to get here to tell us. But that question itself has an unknown answer right now.
Yep. That's I have to start. I think it rises because of our time difference. I have to see if it's 1 o'clock for us as well, so I can start taking my winter images as I usually do when Orion rises. I stop looking at just about everything else, and I'm also hoping to get a better image of that Milky Way, the winter Milky Way as it runs by it. That's tough, but that's going to be my target for this winter. So let's see, Kenneth Burton has come back with another question. Speaking of stars, as to the makeup of large OAB stars, given their obvious young age and then them being made up of the stuff left over from supernovae, are they rich in the heavier elements like our G-class star, our G-class sun?
I'd like to suggest Jane or Larry to tackle that.
You're right. I mean, basically, most of the star things like O and B stars are fairly young stars, so they're made up of material that has probably been reprocessed multiple times since the formation of our galaxy. All these stars that we're seeing are in our galaxy. So if they're second, third, fourth, fifth generation stars, yes, they're going to have a lot of heavy elements in them.
Yeah. So to be clear, all stars are mostly hydrogen, but but we do know that they have heavy elements in them because you can use something called spectroscopy, which is where the atoms change energy levels at characteristic wavelengths. So you can basically fingerprint those atoms and find them when you look at how the light from the star changes as a function of wavelength. That's called a spectrum.
Okay.
The interesting thing about Betelgeuse is that it has reached the point where it's starting to fuse heavier and heavier elements. And when a star starts to get heavier and heavier, they fuse faster and faster until you get to iron. And that is a wall. And once it tries to fuse iron, iron will not fuse. And then the star just simply collapses on itself. And then that collapse might take a few tenths of a second or something like that. And then the atmosphere of the star simply explodes into space. And then you have a supernova. And Betelgeuse is pretty darn close to that right now. But pretty darn close in a star's lifetime could mean anywhere from a few minutes to hundreds of thousands of years. But certainly I would think that in the next several 100,000 years, Betelgeuse will become a supernova and it will lighten the sky. And we certainly will all know about that when it happens. It'll be visible in broad daylight, and it's coming. It's in our future, but whether it's within our lifetime now, it probably is not. But
Well, if it does happen, I would like to hope it happens in the northern hemisphere and not when it's visible in the southern hemisphere and we don't get to see it. But I know we can't predict that.
well, if it's Betelgeuse, it certainly will be in the northern hemisphere. We'll be able to see it. It's another
True.
star, maybe not.
Yeah. Well, now Jim Forrester has a good question concerning planning for dark matter and dark energy. His question: once the LHC was funded, scientists had high expectations for the Higgs boson particle would be detected. The same with LIGO and gravity waves. Are there any projects in planning for dark matter and dark energy?
There
That's
is
one for
a-
Jane.
Go on, Jane, if you want to.
Yeah, there are lots of projects in progress related to dark energy and dark matter. So for dark energy, there's something called the Dark Energy Survey, DES, which is basically going to, or is it called DESI? Sorry.
DESI.
It's called Dark Energy Survey. Like there's the telescopes that are going to survey tons and tons of galaxies. Similarly, dark matter, there's something called the Dragonfly telephoto array that right now I think is looking at ultra diffuse dwarf galaxies. And the reason those are unusual is because they seem to have, some of them seem to have way less dark matter than what ordinary models of galaxies would imply. So that's on the astronomical observation side, which I'm more familiar with. But my understanding is that there are also lab experiments that are happening on Earth as well.
Okay. Let's see. We have another question from Kenneth Burton. I have heard somewhere that no star has less than 24% helium. Is that true?
I would doubt it, because I think that a very young star would be, wouldn't it be true? Jane and Larry, correct me if I'm wrong, which I probably am, but wouldn't a very young star be almost entirely hydrogen? And then they build up their supply of helium over their lifetime. So I don't think there's a legal lower limit of helium for a star. But I may be wrong.
Yeah, I think that's a correct statement. I mean, there are some stars that appear to be as old as the galaxy, so we're talking 12 billion years old, give or take a bit, and those are going to be mostly hydrogen with very little helium in them, I would guess.
A star's composition changes throughout its lifetime, as was alluded to in when David's comment about the supernovae. So a star gets its power from hydrogen. Hydrogen is, by far the most common element in the universe. The hydrogen fuses into helium, and that fusion gives off energy. That's why stars shine. And then you keep building upward. Helium, also like then you start getting stars that have more carbon, have more oxygen. For the most massive stars, for the more massive stars, they have enough energy to go up to iron, and that's when they explode into supernovae. For something like our sun, eventually it'll become a white dwarf. That would just be like the dying core of a star, and that would be carbon and oxygen rich, because you've burned out your hydrogen, you burned out your helium, and then you're just left with the heavy elements left over from the fusion process.
Thanks, Jane. I think I can also add that the Internal Revenue Service has proclaimed that stars with less than 24% helium, or whatever number you gave, do not have to pay taxes this year.
I need to earn more money. Just doesn't help to just act like celebrity. I guess I got to actually do something to make me a celebrity. So I'll go figure something out. So I actually had a question. We were talking about Betelgeuse and how it looks like it's going to go kablooey. Maybe not any in our lifetimes, but it's definitely active. There was another star that I had learned about, Eta Carinae, which in the southern hemisphere, which I thought was undergoing some very similar process where it was very active. Any updates on that star, or is it still exhibiting similar characteristics to Betelgeuse?
Actually not. It's a good question. I'm glad you brought up Eta Carinae, but that was the star that Bart Bok was working on during much of his time in the southern hemisphere. And I think if he were here, may you rest in peace, he were here, he would be able to answer that question a lot better than I would. It's just a very, very large star. And in the 19th century, it suddenly got bright, started to become brighter and brighter and brighter. And I think at its maximum was like third, or it got to as bright as -1 or something like that. But it was not a supernova, and it still exists. And it still is humming around there at about third magnitude or so. But I, as to why it's doing that, I really don't know. So I took a long time there out of everyone else's time to say I don't know, but I really don't.
That's fine.
It's a very, very fascinating object in the sky.
No,
And
that's
if you
good.
go to the southern hemisphere, you go to you look at Alpha Centauri, Beta Centauri. You look at you look at the dark area that is next to the Southern Cross, and then right after that is Eta Carina. It's a beautiful, beautiful arm of the southern sky, which I really enjoy looking at. And I remember pointing it out to everybody on in November of 2001. And while I pointed it out to everyone, there were 3 or 4 meteors that were visible in that area of the sky. And that was during the Great Leonid meteor shower and storm of 2001. And that's about all I can say about Eta Carina. It's a lovely, lovely object to enjoy in the sky, southern sky.
Okay, and again, it just means I need to get to the southern sky, take my camera and telescope with me, and spend about a month.
And please let me know when you go so I could try to join you.
I will. We're waiting on travel restrictions to be lifted, and for me to work my finances a little bit better. So
Yeah.
I think maybe they'll converge at the same time. That would be nice. But I definitely want to go. Kenneth Burton is asking, is Antares currently at risk? And how about S Dorados? 2 more large stars that we think is maybe nearing their times.
I don't think they're anywhere near getting ready to go to the red giant phase or anything like that. Not that I'm aware of. I mean, as David was saying, that on the time scale of star lives versus our lifetimes, we're talking, a long time from now. So Betelgeuse is probably in the near vicinity. That's the one we should be watching for.
Okay, so looking at the time, it's 8:55. I think you did get started right around 8 o'clock, which is what I had hoped for, because then we would have the full hour. So we're near 5 minutes away. So for those on the chat, we'll give you a couple more minutes to drop a couple more questions. Of course, we want you to fill out our survey. For Astronomy on the Beach, let us know what you think about not only this panel, but all of the programs that we've had. I'm going to throw in a question that doesn't necessarily require mathematics. It's about life of a professional astronomer, and specifically, how much of your work, as far as enjoying your work versus getting a chance to do some of the things that we as amateur astronomers do and just simply look at the night sky. How do you all balance that?
For me, everybody is different. You have professional astronomers who spend a lot of their time going out and observing with large telescopes, to the point where many of them actually are staying at home and observing remotely. And some of them are also amateur astronomers on the side. Some of them are not. And in many respects, there are amateur astronomers who have substantially more skill at observing than some of the professional astronomers. And yes, I enjoy, I mean, I do not do a lot of going to, well, what used to be big telescopes, but are now medium-sized telescopes because there are bigger telescopes that have been built. But basically, I still appreciate more going out and, naked eye, looking through a telescope with my eye, looking at the night sky, just appreciating it. And David probably does a lot more than I do. But yeah, there are a lot of my associates who really have no appreciation whatsoever for the night sky. Unfortunately, they in some cases they're not observational astronomers. They're mathematicians or theoretical physicists. So how do you balance that?
And how about you, Jane?
So my research uses radio astronomy, and since we can't see radio waves, my working time does not generally involve looking at the night sky. But I do like to get involved in outreach events that involve observing. So when I was in grad school, for example, I did something called the Harvard Observing Project, where grad students would lead small groups of people who are not professional astronomers, or students or other researchers who happen to be part of the university community, and take them up to the telescope that was on top of the roof of the Science Center and look at things like asteroids, stars, the moon, planets. And that was a fun way to use hands-on observing experience to teach the public about astronomy. And I think each grad student participant program usually did that like a few times a semester.
And I am not, by any remote possibility, a professional astronomer. I am an amateur astronomer. And I think the best way I can express this is through the following quotation by a well-known astronomer. "Our fondness for the stars has touched our souls. We all share the feeling of discovery, whether the object we have found is new to all or new only to us. The thrill penetrates our being as we try to describe, through drawings, photographs, or words, how we have been changed by the universe sharing a secret with us."
So apparently an alarm is going off for some reason.
That's telling you, didn't you attended the session this morning where we were told, you would get an alarm that says the session is over.
Okay, so I think that's what's going on. But even though the session's supposed to be over, I'm going to honor the final question by Same Old Dog, because he asked, what is your greatest expectation from the James Webb? And I feel it's worth it to give his question a shot before we wrap up. So what is your greatest expectation from the James Webb Space Telescope?
For me, as a planetary scientist, and I suspect, Jane, it's the same situation, is the capability of the James Webb Telescope to study in more detail planets around other stars. Because we are, even though we know there are 4,000, or we've found 4,000 or 5,000 of them now, we're just learning about them. Our ability to study them now is probably equivalent to 50 or 100 years ago of our studying the planets in our own solar system. So with the James Webb Telescope, I think its capabilities of looking at the atmospheres of planets around other stars, and however, I'm not sure all the different ways in detecting new planets, I think to me is a more exciting thing, is finding up, looking at, I want to say this, looking at planets we know about around other stars and being able in more detail to characterize their atmospheres. And by characterizing their atmospheres, it gives us an idea of whether or not there might be life on those bodies. I think that sums it up more succinctly.
Jane?
Yeah, so atmospheres is definitely going to be one of the most exciting things that James Webb can do. Another interesting thing that we hope it will be able to do well is finding newborn planets. So those are possible to find on the ground right now, but very difficult. So we don't know a lot about the sort of distribution of where, when, and how planets form. So James Webb, it will be very sensitive, and you don't have to deal with the atmosphere. So we're hoping that it will find more newborn planets. Almost all the exoplanets that people know about are, very old, like billions of years old. So they've had a lot of time to evolve, and we want to know more about how planets actually form.
You can do all your modeling of planets, but the best way of finding out how planets form is to see them in the
My
process
answer
of
to
forming.
that question, Larry and Jane and Adrian, is that if and when James Webb finally launches, my goal is that it works. If it works, Wendy and I will be dancing a horror around our backyard if the thing launches and it actually works. That's all my hope is for. Whatever it discovers. And I think the things that it will discover will be things we can't even imagine right now. And if it works, I'll be dancing.
I think that's my thing too. Of course, I've watched and listened to talks about it online, and I was reminded of a satellite that there was so many high hopes for it, and then there was a malfunction where the capsule that contained it would not jettison, and the satellite began opening up inside of that capsule, and it was just I could imagine how horrid that felt to know that this thing was breaking apart, trying to open up like it was supposed to, all because the capsule wouldn't eject. And so definitely hoping that is not the fate of this telescope, that everything works well. I'm sure all the tests will be done and are still being done. And I know that there's been a lot of delays. So 2021, we hope all of those delays are finally pushed through, that everything looks good, and that it finally does launch. Probably.
Sorry,
go ahead.
I was going to say, building on what David said originally, is most of the most exciting discoveries are the ones you didn't expect to discover. Yeah. It's always great to go find something that you were expecting to find, but it's much more exciting to go and find I don't understand what I'm seeing. This is curious. It excites you. It opens up whole new areas of physics and astronomy and geology, etc.
I'm thinking right now of a night back in the late 90s when Larry and Nancy and their daughter Miranda came down to our home with Wendy and me and just looked through our telescope and just looked up at the night sky. Those were just wonderful memories that I cherish.
We remember them.
Okay, and I think with that, we are all done. Any parting comments from our panel?
I want to thank the people on YouTube for their questions, most of them out of my field of expertise, but we won't go there. But yes.
Go ahead, Larry. Finish. You can finish up. And I should probably be calling you Dr. Lebowski, Dr. Wong, and Dr. Levy. You told us the story of how you got your doctorate.
Dr. Larry is what I go by if you want to be formal.
Okay, Dr. Larry. And my wife is not into astronomy, but her PhD, should she receive it, she defends on the 30th in education. So even she would be a doctor. We're hoping all goes well with that. And of course, I'm I'm skipping work and everything else to make sure I'm available to watch the defense. So
I wish her luck, and yes, to me, education is what I do now I am an educator now, or I pretend to be an educator now, because I try to get the excitement of the science I used to do and the science that's occurring now across to teachers, educators, Girl Scout leaders. That's pretty much what I do now.
And Dr. Jane, Dr. Larry, Dr. Adrian, thank you for setting this up. This was so much fun.
I enjoyed it.
Yep. I would be remiss if we didn't tell those who are left about Dr. Levy's book. It's available, and go ahead and show us A Night Watchman's Journey. If any that are in clubs are interested in purchasing this, we can work directly with David Levy and his wife. You all are welcome to, and I'm swatting away a gnat. That's why I'm doing that. You all are welcome to send me an email or contact me and say, we would like a copy of the book. I can put together an order and send it directly to David, and we will buy the books. I'm going to buy one, so you all are welcome to join me if you haven't already bought it. Kenneth Burton says he's already got one, and I am in need of purchasing it, so I'll be doing that. So I had to shamelessly help David plug the book, and if there's anything, Dr. Larry, Dr. Jane, that we should shamelessly plug at this time,
No.
let's do it. Otherwise, I'm going to go join my session, which is 8 minutes behind, but it's okay. I'm doing a session on star hopping with stellarium. So I'm basically going to ask folks, what do you want to see an image of, and using stellarium to go out and get it and answer questions. So that's all I'm going to do. And Justin Doring trying to sneak a question in. This may be off topic, but I use binoculars for my sky viewing hobby, and I am having a problem with my lenses fogging up, even if I don't hold them directly to my eyes. Any advice to not get fogged out?
I don't think you can have a better instrument than a pair of binoculars.
Yes.
Larry?
I was going to say the only thing I would recommend is go to a place with lower humidity.
Yeah, Justine, that happens to me often. I also, and I think I replied to your comment on it on the binocular astronomy piece. If you leave the binoculars out so that they acclimate to the temperature that you're going to be observing in, I believe they're less likely to fog up.
That
of course,
is
once
correct.
you put them to your eyes,
Yes.
your body.
It's true of any telescope.
Yeah.
Well, I've got to
so
go
if you
back
wanna
to
observe-
another session that I'm on. So.
Yeah. So, all righty. We're going to go ahead and end the stream. Thank you all for joining. Thank you, professional astronomers.
Thanks, Jane. Thanks, Larry.
Take care, Levy. Say hello to Wendy, please.
I will. Wendy says hi.
All right. Thank you all. The stream
Thanks
is
so
now ended. And I'm going to